In this video, we're discussing about heat exchangers. In the heat exchangers, we're discussing about double pipe heat exchangers with parallel and counter flow. Okay. First of all, we are checking with the results parallel flow, and then after counter flow, and we're discussing that what will happen. Okay. So first, before that, I have created a design with the help of SolidWorks with real-time applications. And see, this is how you develop your design based on the dimensions. Okay. And these are the dimensions which I have followed. And then later, see, this is your assembly process, and now you used ANSYS process. In this process, you used steel and aluminum, steel and EN9 material. It is nothing but like EN9 also is a kind of steel material. Okay, so forged steel, like carbon steel, it's kind of okay. The reason behind it why I choose this because the yield strength. So it is look like similar to the steel material, but it has the better properties than the steel. That's it. Okay, and you imported them and you used machines and you applied some kind of pressure inside, and you want to know the results of this object, like how much pressure it can withstand. Okay, the maximum amount of pressure it can withstand maximum is 5 megapascals, and the results have been shown here, like steel is deformation, and red color indicates the highest value, blue color indicates the lowest value. Okay, after completing this, and you got to know that steel and EN9 material, in between them straight factor is highest for this 2.21 1:1 for EN9. Okay, so EN9 is the best among steel. And now what you are doing here, you are doing analysis with CFD results. So in this process you used water first of all, and then next you used water with nanoparticles, which is 0.025% of nanoparticles. It means when you mix water with 0.025 nanoparticles and you got these properties, then next is water with 0.1 nanoparticles. Okay, and this outer body is considered as a outer, like a cold inlet. I mean, it is nothing but a cold domain. The inner pipe is considered to be as a hot domain. Okay, and you have mentioned is a cold outlet, and this is a cold inlet, this is a cold outlet, and similar case hot inlet, hot outlet. Okay, so now you mentioned each and every domain, cold domain and hot domains. Okay, and now you have applied, this is the like cold temperature and hot temperature, and this is the cold mass flow rate. Okay, and now the hot mass flow rate, this is, and you have got the results like pressure values. Okay, how much pressure you have here, this is the maximum pressure value and how much pressure it has, and you knowing that. And for the each and every domain, like for inner and outer also I have mentioned it. Then later you also calculated the inlet and outlet temperatures for the each domain. Okay, these are the domains for each inlet and outlet, and this is the heat transfer for the each domain, cold domain and hot domain. Okay, so when you used water with aluminum, what happened? Okay, that means when you're using nanoparticles instead of when you mix the nanoparticles in water, what is the changes? Okay, so now we discuss all those things in a separate graph. So this is the graph. Okay, and till now we discussed only parallel flow results. Now we are analyzing the counter flow results, and the same boundary condition will apply on this. Then later, now we need to understand these both conditions, like which is the best among them. So these are the results for the counter flow, and now there's the graphs and everything like this. Yeah, this is how you compare your results. So I'll show you this. See for this pressure. Okay, leave it about pressure and everything. I just want to check that cold outlet for the water, it has 309. While it is cold outlet increasing, it is increasing. Hot outlet check 311, 310, 310. Okay, while increasing these nanoparticles, the hot outlet temperature has been reducing. It is nothing but heat dissipation rate has been increased. Okay, the similar way for counter flow also, you're checking that cold outlet 325, 330, 330, hot outlet 298, 299, 299. Okay, and you comparing this same thing, and finally giving on conclusion among these which is the best one. See, finally we are we are concluding that aluminum, Al2O3 nanoparticles are increasing the heat transfer rate values in parallel flow and decreasing in counter flow. So this is what you observed. Okay, while using this nanoparticles, each and every time it's not increasing the heat transfer rate, but In parallel flow it is increasing, in counter flow it is decreasing. So 0.025 with aluminum and 0.10 and Al2O3 nanoparticles are suggested for only parallel flow heat exchanger to enhance the heat transfer rate values. That's it. It means you conducted that one project on this, how it behave, like how the behavior will change when you use parallel flow and counter flow. Basically, when you're using this aluminum like nanoparticles, some amount of percentage. So this is how you conduct. Okay, and these are the designs. See, this is the design. Okay, and next videos I will tell you what if I add. In previous case, like in this case, I have not added any internal protrusions. See, if you look at this, there is no internal protrusions. It is completely plain tubes. Okay, now I have developed one more concept which is having the internal protrusions. It means it will increase the heat transfer rate more compared to the previous one. Okay, because it is having here protrusions, so it takes some time to reach other level. That means it need to spend some more extra time. More extra time is nothing but it spend more heat transfer rate. So I have created one more design like this. So we'll check about these results in next or some other videos. Stay tuned for these kind of videos. Thanks for watching.